In our previous video, we built this battery and we named every part. Now we want to answer the question, how does a battery actually store and release energy? It actually all comes down to chemistry, and fortunately, you don't necessarily need to be a chemist to be able to understand it. You just need to know about what happens to three things in the battery: the positive plates, the negative plates, and the electrolyte. Okay, so let's start by identifying the three key players. Player one is this positive plate. It's coated in lead dioxide, PbO2. When fully charged, this material is ready to accept electron. Player 2 is the negative plate paste. It's coated in sponge lead, Pb. When fully charged, this material is ready to release electrons. Player 3, the electrolyte, is a mixture of sulfuric acid and water. This is the chemical bridge between the plates. It carries ions back and forth during charge and discharge. Cell 1's label explains the electrolyte's role. The electrolyte's role is to carry ions between positive and negative plates. It also enables reversibility of the chemical reaction. We want to be able to discharge this battery and recharge the battery. It acts as an energy transfer medium. So we want to be able to transfer the energy between the positive and negative plates. The electrolyte serves as a direct indicator of the battery's health. When you turn the key and crank the engine, current flows. Here's what's happening in each cell. Electrons flow from the negative plate through the external circuit, for instance, your starter motor, and into the positive plate. That flow of electrons is your electrical current. At the same time, sulfate ions leave the electrolyte and bond to both plates. The positive plate's lead dioxide becomes lead sulfate. The negative plate's sponge lead also becomes lead sulfate. Watch the plates change color. Both plates are converting to lead sulfate. They're becoming the same material, and the electrolyte is getting weaker. Less acid, more water. Here's the overall reaction. Lead dioxide plus sponge lead plus sulfuric acid gives us lead sulfate on both plates plus water. The acid is consumed and water is produced. That's why a discharge battery has thinner electrolyte. I will include a link to this animation in the video description. You can also download it on our page and explore it yourself. Now we can connect a charger or the alternator to reverse this chemical reaction. Current is pushed back into the battery in the reverse direction. Electrons now flow from the positive plate through the charger to the negative plate. This is the opposite direction that we saw during discharge. The sulfate ions detach from both plates and return to the electrolyte. The sulfuric acid is being regenerated. Watch the plates change back. The positive plate converts back to lead dioxide. The negative plate converts back to sponge lead. And look at the bar graph. The acid concentration is rising while the water decreases. Here's the reverse equation. 2 lead sulfate plus 2 water gives you lead dioxide, sponge lead, and sulfuric acid. Water is consumed, acid is regenerated. The battery is fully restored. This animation is also available for download on our website, and I'll include a link to the URL if you just want to use it in the browser. Since the acid concentration changes with charge state, we can actually measure it to determine how charged the battery is. That measurement is called specific gravity. How dense a liquid is compared to pure water. Water has a specific gravity of 1.0. Sulfuric acid is heavier, so charged battery electrolyte has a specific gravity higher than water. If we look at this graphic on the left, the charged electrolyte is 36% acid. This gives us a specific gravity of 1.265 and an open circuit voltage of 12.6 volts. On the right, after discharge, it's mostly water. Specific gravity drops to 1.120, voltage drops to 11.9 volts. The gauge in the middle shows how specific gravity and voltage track together as the battery discharges. You don't need to memorize these numbers. The important thing is the pattern. As the battery discharges, acid gets weaker, specific gravity drops, and voltage drops with it. Now, some batteries give you a way to see this change without any tools. Look at this indicator window built into the top of the battery. It's called a built-in hydrometer or charge indicator eye. Inside one cell, there's a small cage submerged in the electrolyte containing a green ball. When the acid is strong, the battery is charged. The dense electrolyte supports the ball and it floats up into a light pipe. You can see a green dot through the window. When the battery discharges, the acid weakens and the electrolyte becomes too thin to support the ball. It sinks to the bottom of the cage. Now when you look through the window, you see dark or black, no green ball in the light pipe. This battery would need charging. There's a third reading. If the electrolyte level drops below the cage from evaporation or overcharging, the window appears clear, or it could be bright yellow. This means that the battery needs water, and it may already be damaged. The limitation of this type of indicator is that it only reads one cell out of the 6. If different cells have a problem, the indicator won't show it. That's why we still need to do other tests like an open circuit voltage test and other tests that we'll describe in the next lesson. Since most modern automotive batteries are sealed, you can't actually access the electrolyte. Using tests like an open circuit voltage will help to determine the charge state of the battery. We will cover the open circuit voltage testing it at a later date. There do exist some batteries, typically not found on modern vehicles, but maybe heavy equipment and diesel applications, where you can measure the individual electrolyte of each of the cells to determine the charge state of the battery. Usually there'll be some type of indication and places to be able to access the individual cell electrolyte that you can service, and the battery will indicate that on it. So let's recap. The 3 critical components of the battery that are involved in charging and discharging are the positive plate, the negative plate, and the electrolyte of the cell. During discharge, both plates become lead sulfate and the electrolyte gets weaker. During charging, the reaction reverses. The plates restore to their original state and the electrolyte gets stronger. We can measure this chemical change using specific gravity if the battery allows us to. We can look at that indicator eye on some batteries that will tell us the state of one individual cell, or we can perform an open circuit voltage test, which we'll be covering in a future video. These tests are really just a way to measure the health of the chemical process that's occurring in the battery. If the chemistry is good, the battery performs. If the chemistry has degraded, the battery will fail. Remember, you can download those animations that I showed you from our website. I'll leave a link in the video description below, and feel free to utilize those. And there is a Canvas course, if you'd like to download that for free, that's also, I'll leave a link to.